Hello students and welcome to the quick solution of All India Cast Test Series JEE Advanced 2019 Test 3A Paper 2 Code C&D Physics. Let's move to question number 1. In question number 1, a narrow monochromatic light beam of intensity I0 is incident on a glass plate. Glass plate reflects 50% of the light incident on it and transmits the remaining. If Imax and I minimum are the maximum and minimum intensity of interference pattern formed by the two beams obtained after one reflection each from the surface of plate, then ratio Imax upon I minimum is equal to. So let's understand the situation. Suppose this is a plate and these are the two surfaces of the plate and some beam is incident with intensity I0. So if it is incident with intensity I0, then half intensity gets reflected. So I0 by 2 goes in this direction and remaining I0 by 2 goes in this direction. Now when transmitted beam falls on the second surface, then half intensity of the beam gets reflected, that is I0 by 4, and I0 by 4 gets transmitted. Now when this I0 by 4 intensity falls on the first surface, then half of the intensity again gets transmitted and half intensity gets refracted. So if I see the transmitted part, then transmitted part will be this, and these two rays are parallel. So the intensity of this is I0 by 8. So if I say this is my I2 let, then the value of I1 is equal to 4 times I2. Now these two beams form the interference pattern on the screen. So if I take the ratio I max by I minimum, then it can be written as under root I1 plus under root I2 divided by under root I1 minus under root I2 whole square. So if I substitute the value of I1 in terms of I2, it can be further written as under root I2 into 2 plus 1 divided by under root I2 into 2 minus 1 whole square. So on solving, it comes out to be 9. So option A is the correct answer. So the correct answer for question number 1 is option A. Let's move to question number 2. In question number 2, a ray of light is incident at a point at an angle of incidence 45 degree on a glass sphere of refractive index root 2. Light ray gets reflected and refracted at the further surface of the sphere. Then the angle between the reflected and the refracted rays at the surface is. So for this, first of all, we draw a glass sphere and a ray of light is incident on this glass sphere at an angle of 45 degree. Let this is an angle 45 degree, angle of incidence. So if this is the angle of incidence, then the angle of refraction is like, let this is R, and let this point is the center of the sphere. Then if I draw the normal, then since these two lengths are equal, then it is also R, and if I apply the Snell's law at point X, then I can say that 1 into sine 45 degree is equal to mu is equal to refractive index of the glass sphere, that is root 2 into sine R. So on solving here, the value of R comes out to be 30 degree. So this angle is 30 degree, this angle is also 30 degree. So if the angle of incidence at this point is 30 degree, then the angle of refraction at point Y must be 45 degree. So I can say that let this angle is 45 degree. Now the question is angle between the reflected and the refracted rays at the surface. So reflected ray is this and it makes an angle of R with the normal, and refracted ray is this. So I have to calculate this angle phi. So I can say that if I see this line, then this angle plus this angle plus this angle must be equal to 180 degree. So I can say that 45 degree plus phi plus 30 degree must be equal to 180 degree. So from here the value of phi comes out to be 105 degree. So option D is the correct answer. So the correct answer for question number 2 is option D. Let's move to question number 3. In question number 3, a point object O is placed on the principal axis at a distance of 15 cm from the convex lens. This separation is given 15 cm. Further, a glass slab having its one face silvered is also placed at a distance of 30 cm from the point object as shown. So one side of the slab is at a distance of 30 cm from the point object. If final image coincides with the object itself, then focal length f of the lens is equal to. So in order that the final image coincides with the object itself, then we can say that the ray retraces its path after reflection from this. So I can say that the ray retraces its path after reflection from this plane mirror. So this is possible when the object is kept at the focus of the lens, then after refraction from the lens, rays become parallel, and as the parallel rays incident on the glass with angle of incidence 0, then it goes undeviated, and from this point it gets reflected. So again they follows the same path and meet at point O, so the final image will form at point O. So we can say that the object must be kept at the focal length of the lens. So the focal length of lens in this case would be 15 cm. So the correct answer for question number 3 is option B. Let's move to question number 4. In question number 4, when a metallic surface is illuminated with a monochromatic light of wavelength 414 nanometer, its stopping potential is found to be V0. So if I apply the photoelectric equation, if I take the value of lambda is equal to 414 nanometer, then I can write SC by lambda is equal to work function phi plus E into V0. E into V0 is the maximum kinetic energy of the ejected photoelectrons. Further, when the same metallic surface is illuminated with a light of 828 nanometer, that is 2 lambda, the stopping potential becomes V0 by 3. Then the work function of the metal is. So for the second part we can write SC by 2 lambda is equal to work function phi plus E into V0 by 3. So this is E. So if I solve these two equations, I get phi. It comes out to be SC by 4 lambda. So if I substitute the value of SC by 4 lambda, SC is 1242 electron volt nanometer divided by 4 into lambda, and lambda is 414 nanometer. So if I solve this, it comes out to be 3 by 4 electron volt. So option C is the correct answer. So the correct answer for question number 4 is option C. Let's move to question number 5. In question number 5, a plane mirror placed perpendicular to XY plane is moving with velocity Vm is equal to 2j meter per second. Velocity of image of object O formed by plane mirror with respect to observer P moving with velocity Vp vector is equal to I cap plus 2j cap meter per second is 4i plus 6j meter per second. If the velocity of object is this, then the value of x square plus y square minus 4y is equal to. We know that in case of plane mirror, the velocity of image with respect to mirror is equal to negative of velocity of object with respect to mirror. So if I take mod of this, I can say mod of velocity of image with respect to mirror is equal to mod of velocity of object with respect to mirror. So this can be further written as velocity of image minus velocity of mirror, and this can be further written as velocity of object with respect to ground frame minus velocity of mirror in the ground frame. So velocity of image in ground frame can be written as velocity of image with respect to some observer P plus velocity of observer P with respect to ground frame minus velocity of mirror, and further it is equal to velocity of object minus velocity of mirror. So if I substitute the data, then velocity of image with respect to P is 4i plus 6j, and velocity of P itself is I plus 2j, minus velocity of mirror, that is 2j, and it is equal to velocity of object, that is xi plus yj minus velocity of mirror, that is 2j. So on solving this, it comes out to be mod of 5i cap plus 6j cap is equal to mod of xi cap plus y minus 2j cap. So if I take the mod on both the sides, then under root 61 is equal to under root of x square plus y minus 2 ka whole square. So on solving this, I will get x square plus y square minus 4y is equal to 57. So option B is the correct answer. So the correct answer for question number 5 is option B. Let's move to question number 6. In question number 6, a diverging lens of focal length f1 is equal to 10 cm is placed in front of and coaxially with a concave mirror of focal length f2 is equal to 15 cm. So let's understand the situation. Suppose this is a diverging lens and it is kept in front of a concave mirror. Suppose this is the concave mirror and both the diverging lens and the concave mirror are placed coaxially. The separation between them is capital D. So this separation is capital D. Further, if a parallel beam of light incident on the lens returns as a parallel beam from the arrangement, then we have to calculate the value of D. Suppose these are the parallel rays which incident on the diverging lens. So after diverging from the lens, they will move in this fashion, suppose, and this line go undeviated. So after passing from the diverging lens, they appears to come from the focus of the diverging lens, and it is given in the question that the focal length of the diverging lens is 10 cm and the focal length of the concave mirror is 15 cm. If the parallel beam of light have to retrace its path, then it must fall normally on the concave mirror. As they fall normally to the concave mirror, angle of incidence is 0, then they will retrace this path, and after reaching to the diverging lens, they will move in this direction. So I can say that this point must be the center of curvature of the concave mirror. So I have to calculate D. So this separation is 2 times mod of f2 and this separation is mod of f1. So in order to calculate D, it must be equal to 2 times mod of f2 minus mod of f1. So f2 is 15 cm minus f1 is 10 cm. So it comes out to be 20 cm. So the correct option is option A. So the correct answer for question number 6 is option A. Let's move to question number 7. In the question number 7, two monochromatic coherent sources S1 and S2 emitting light of wavelength 4000 angstrom are placed along the line normal to screen as shown in figure. Separation between S1 and S2 is D, which is equal to 1 mm. If capital D is equal to 1 meter, then order of bright fringe formed at point O. So for the bright fringe formed at point O, path difference delta x at point O must be equal to m into lambda. So the path difference between the two sources S1 and S2 is D. So D is equal to m into lambda. So the order of bright fringe m is equal to d by lambda. So if I substitute the data, the value of d is 1 into 10 to the power minus 3 and the value of lambda is 4 into 10 to the power minus 7. So if I solve this, it comes out to be 2500. So the order of bright fringe is 2500. So option A is the correct answer. So the correct answer for question number 7 is option A. Let's move to question number 8. In question number 8, A parallel monochromatic beam of light of wavelength 6000 angstrom is incident on two slits separated by a distance of 4.5 into 10 to the power minus 4 meter. A glass plate of thickness 2 into 10 to the power minus 7 meter is placed in front of S2 as shown. If resultant intensity at point O is I0, where I0 is the intensity due to each slit, then refractive index of the glass plate is equal to. So it is given in the question that the resultant intensity at point O is I0. So this is possible when the phase difference between S1 and S2 at point O must be equal to 2 pi by 3, because the resultant intensity is I1 plus I2 plus 2 root I1 I2 cos phi, and the value of I1 I2 and resultant intensity is same. So on solving we will get phi is equal to 2 pi by 3, which is the phase difference at point O due to sources S1 and S2. So if I write the path difference at this point, the path difference delta x at this point is due to, because of this introduced slits, and that is equal to t into mu minus 1. So I can say that phase difference phi is equal to 2 pi by lambda into path difference delta x. So if I substitute 2 pi by 3 is equal to 2 pi by lambda into delta x, that is t into mu minus 1. So if I solve this, the value of mu comes out to be 1 plus lambda by 3t. So if I substitute the data, mu is equal to 1 plus the value of lambda is 6 into 10 to the power minus 7 divided by 3 into t, that is equal to 2 into 10 to the power minus 7. So if I solve this, it comes out to be 2. So option B is correct. So the correct answer for question number 8 is option B. Let's move to question number 9. In question number 9, two radioactive materials A and B have decay constant 50 lambda and 10 lambda respectively. If initially they have the same number of radioactive nuclei, then the number of radioactive nuclei of A to that of B will be 1 by E after a time t is equal to t0. Then the value of time t0 is. So it is given in the question Na divided by Ne, that is the number of radioactive nuclei at time t0, is equal to e raised to the power minus 1. So Na at any time t0 can be written as n0 into e raised to the power minus 50 lambda into t0 divided by Nb at any time t0 can be written as n0 into e raised to the power minus 10 lambda into t0 is equal to e raised to the power minus 1. So on further solving, I can say that e raised to the power minus 40 lambda into t0 is equal to e raised to the power minus 1. So on comparison, we will get the value of t0, and it is equal to 1 upon 40 into lambda. So option B is correct. So the correct answer for question number 9 is option B. Let's move to question number